So here we've got a second order differential equation and we want to solve it. So first we'll start by forming the auxiliary equation in order to evaluate for the solution of the main bulk of the equation. So we're going to use a variable m to denote the order of the differential. So m squared for the second differential plus m for the first minus 2 for just the equation itself is equal to 0. So when we factorize this, we get m minus 1 times m plus 2 is equal to 0. So we get m is equal to 1 and minus 2. So now we plug these into our complementary function, which is going to make the bulk of our equation. So we have y is equal to a e to the x. So that's the first root times x plus b e to the minus 2x. That's our second root times x, where a and b are constants. Now we use our particular integral and we try to find the extra addition that we add to get the 12e to the minus x. So we'll try y is equal to, we'll do k e to the minus x, since we've got the similar expression in the actual equation. So now we do y dash is equal to minus k e to the minus x, and y double dash is equal to just k e to the minus x, since the minus comes down each time. Now we plug these back into the original equation and we solve to get what k is. So we've got one of each, so we've got k e to the minus x plus this, so minus k e to the minus x, minus 2 of y, so minus 2ke to the minus x equals 12e to the minus x. So these two cancel, and then we can divide through by e to the minus x, so we get minus 2k equals 12, or k is equal to minus 6. So now our general solution is as follows: y is equal to a e to the x plus b e to the minus 2x minus 6e to the minus x, as you can see. Now, what we need to do is find out what the constants are for the particular solution. So the question tells us that dy dx is equal to 0 at x equals 0, and as x tends to infinity, y tends to 0. So we can use the second expression, the second statement, and automatically tell that a is going to be equal to 0, because if e to the x, if x tends to infinity, e to the x is going to tend to infinity as well, but y tends to 0, so there can't be an infinity term here. So that means a has to be 0, and there can't be that term there. And we can see that if x tends to infinity for these two, they just tend to 0, so that's fine. Now we'll have to evaluate the first differential and calculate what b is. So we can say that dy dx is equal to minus 2b e to the minus 2x plus 6e to the minus x, and when x equals 0, this equals 0, the whole expression equals 0. So minus 2b times e to the 0 is just 1, plus 6 times e to the 0 is 1, this equals 0, which means that b equals 3. So now we can plug that into our thingy and get our particular solution. So particular solution is y equals 3e to the minus 2x minus 6e to the minus x. So now the final part of the question wants us to find what the value of x is when y equals 0. So 0 equals 3e to the minus 2x minus 6e to the minus x. So we can factor out 3e to the minus x from both of these. So 0 equals 3e to the minus x times e to the minus x minus 2. And since this expression here can't be equal to 0, since there's no power you can put on e to get 0, this expression here must be equal to 0. So e to the minus x minus 2 equals 0, or e to the minus x equals 2. So if you take logs of both sides, minus x is equal to the natural log of 2, and then x is equal to minus ln 2, which is also equal to the ln of a half.